Okay, we have another topic. This is called friction. Of course, we've already kind of talked about friction a little bit. You may remember when we did the PhET simulator, our forces in 1D, we had turned the friction on, and we saw that there was always going to be a force that then opposed it, and we started to talk then again in terms of a net force. And so friction is just one of these forces that we have to deal with all the time in our world. And it's because we can never escape the amount of contact between surfaces. I did choose this picture because I think this is a good representation of actually seeing some friction involved without actually seeing it, but you can see that there was definitely motion involved and that there was an opposing force into it. So let's get started with friction. So the question is what is friction? Okay, and I chose a graphic here that says I want the box to move in this direction, so friction has to act opposite. And so basically this is what we kind of talked about even in 9th grade, was that friction is a force that acts on an opposite direction of the movement, okay? And I'm just going to walk through a few of our main points now, things that we need to know about friction, okay? Friction is what tends to slow down the motion of the object, okay? It's the reason why when we roll a car down a ramp, eventually the car is going to come to rest, okay? We're not imparting any other forces on it except for that frictional force between the wheels and, say, the track that it's on. And that's where we actually look at the motion gets slowed down. And we can then determine that rate of deceleration by looking at where the velocity was before to where it stops. And that's kind of what we're doing with our Matchbox cars in one of our activities. It does act in the direction opposite that motion, okay, so it's always going to be, say, a negative value if we consider the direction that the cart or whatever it is that's moving is the positive. So if we're going in the positive direction, the frictional force acts opposite it. It generally has a negative value to it, and that just the negative value tells us that we are going opposite. Friction really does depend upon the surfaces that are in contact, and we get a different amount of frictional force depending upon what those surfaces are that are in contact. In Minnesota here, we obviously are aware that ice is slippery, okay? And so ice has a very low ability to cause friction between, say, your shoes and the ice, okay? So there's a very low amount of friction there. But if we go and step onto, say, the sidewalk, okay, which is made of concrete, there's a high amount of frictional force between the concrete and your shoe. And so that's one of the things that we start to look at. Now we are going to do an activity, U for your shoe, where we're going to determine the coefficients of friction for a couple of different surfaces between, say, your shoe. Okay, and so that's something that we'll actually look at too. Friction is kind of the amount of friction that we have really depends upon, again, those surfaces, and to figure out that amount of friction, we look at it in terms of the ratio of the friction force to the normal force, okay? And so we're creating a fraction. And whenever we do this, we get a proportionality constant, and that constant is actually referred to as the coefficient of friction. And so that's what this guy is here, this little Greek letter. It stands for mu, it's a Greek symbol, and it stands for the coefficient of friction. And that coefficient of friction is defined as the frictional force divided by the force normal, okay? And so that's the way that we kind of get it. This actually does give us kind of an equation. So if I write out my equation, it's mu is, again, proportional to the force of friction over the force normal. Okay? In other words, friction forces is just the coefficient of friction times the force normal. Okay, so we can actually rearrange this to get the frictional force by itself. So friction force is equal to a coefficient of friction times the force normal. Okay, so that's how we can always determine a force of friction is based off of that. Now this is one of the important things to also note is that, again, friction only matters between the two surfaces that are in contact, okay? Not the area of contact. And then that was one of the things that we try to look at, is that it doesn't make any difference if I put the object like a block on its side or its edge or its end, and I pull it, I'm going to get the same amount of frictional force at any point in time, because again, the way we figure friction forces is just based on the coefficient of friction, which is surface dependent, and then the force normal, which is always going to be the same no matter which side I rotate that block on. Okay? We will really study kind of two different scenarios when it comes to friction. Okay? We have the first one, which is called static friction. And a static friction is this. It's the friction that happens when we are not quite moving. Okay? And so there's a bigger coefficient of friction to try to get an object started moving. And then there's the kinetic friction. And then the kinetic friction is what happens when we're actually moving. So there's two different amounts of friction. What I have here is I have the picture of the sled that we use in a football drill. And it takes more force to get this sled started moving, but once it's moving, it's easier to push. And that's really what we're talking about. The frictional force due to static friction is greater than the frictional force due to kinetic. Okay? So this one is always going to be the bigger of the two types of frictional forces because it takes more to get it started. Now typically what we do is we usually see the symbol mu, and they put like S behind it, which stands for the coefficient of friction of static, or we'll see mu with a K behind it, which means that we're looking at it in the kinetic sense. And again, the coefficient of friction in the static sense is always going to be greater than the coefficient of friction in the kinetic sense. And so there's usually a table that we'll look up and we'll say, well, what is the coefficient of friction for, say, a wood block on a wood table? Okay, and we'll figure that out. Or we actually determine that by pulling objects and measuring the amount of friction force. Okay, so there's our two main scenarios or things that we look at when we look at frictional forces. Now, again, we are talking coefficients of friction, and there's always going to be a way that we can do it. One of the ways that we would figure out a coefficient of friction is we'd actually pull an object, and we would measure the amount of frictional force it took to pull that. If we pulled it at, say, a constant amount, that's what we're going to do with our shoe. The other thing that we can do is we can look at it in terms of as we put something on an incline and we change the angle of the incline, eventually the amount of gravitational force that's down the incline will actually balance out with the frictional force that's holding the object on the incline. And so that's kind of what I've got here in this little picture, and I'll kind of explain what's going on again. You can see that we've got our free body diagram, so there's our center point of our free body diagram, and we have the block's weight acting down. Okay, they did split it up into the components, or the force parallel and the force perpendicular. Okay, so the force perpendicular is mg cosine theta, and the force parallel is mg sine of theta. Okay, and so that's how we get these two components. When we look at balancing this out, and so we want to talk about this in terms of having the velocity be constant. Okay, that means that the net forces are equal to 0. So in other words, my force normal is equal to my force parallel. They're going to be equal to each other because I'm not moving my box one way or another. That's the stationary part. And the force of friction is going to be equal to the force parallel, which means that the motion is going to be constant. There's no acceleration. Now, if I look at that in this sense, my force of friction is the coefficient of friction times the force normal. Well, the force normal is nothing more than mg cosine theta. So in other words, my coefficient of friction times my mg cosine theta is going to be equal then to my force parallel, or mg sine theta, which if I wanted to then look at it in terms of what is the coefficient of friction, so I'm going to solve for that, I would divide both sides by an mg cosine theta, divide by an mg cosine theta, and I can see that another way to look at coefficient of friction is now the sine of theta over the cosine of theta, or the tangent of theta. Okay? So if I can look at an angle, and this angle is only going to be good when the object starts its motion. Okay, so that's where I could put a block on an incline, raise the incline, and the moment that the block starts to move, that's when I know that I've exceeded my coefficient of friction for the static sense. Okay, and so that's another way to kind of look at it in terms of it. Again, we're looking at balancing the two forces. All right, so I have a couple examples, and what I'm going to do here is I'm going to kind of stop my video at this point and do the two examples as a separate video because I know that I'll run out of time. All right.